Section 10.7, Kinetic Molecular Theory. The ideal gas equation describes how gases behave, but it does not explain why they behave as they do. Why does a gas expand when heated at constant pressure? Or why does the pressure increase when a gas is compressed at constant temperature? To understand the physical properties of gases, we need a model that helps us picture what happens to gas particles as experimental conditions such as pressure and temperature change. Such a model, known as the kinetic molecular theory, was developed over a period of about 100 years, culminating in 1857 when Rudolf Clausius published in complete and satisfactory form of the theory. The kinetic molecular theory, the theory of moving molecules, is summarized by the following statements. 1. Gases consist of a large number of molecules that are in continuous, random motion. The word molecule is here to designate the smallest particle of any gas. Some gases, such as noble gases, consist of individual atoms. 2. A combined volume of all the molecules of a gas is negligible relative to the total volume of the gas it's contained. 3. Attractive and repulsive forces between gas molecules are negligible. 4. Energy can be transferred between molecules during collisions, but the average kinetic energy of the molecules does not change over time, as long as the temperature of the gas remains constant. In other words, the collisions are perfectly elastic. And 5. The average kinetic energy of molecules is proportional to the absolute temperature. Any given temperature, the molecules of all gases have the same average kinetic energy. The kinetic molecular theory explains both pressure and temperature at the molecular level. The pressure of a gas is caused by collisions of the molecules with the walls of the container, as shown in Figure 10.17. The magnitude of the pressure is determined by both how often and how forcefully the molecules strike the walls. The absolute temperature of a gas is a measure of the average kinetic energy of its molecules. If two different gases have the same temperature, their molecules have the same average kinetic energy. Statement 5 of the kinetic molecular theory. If the absolute temperature of the gas is doubled, the average kinetic energy of its molecules doubles. Thus, molecular motion increases with increasing temperature. Figure 10.17. The molecular origin of gas pressure. The pressure exerted by a gas is caused by collisions of gas molecules with the walls of their container. Distributions of molecular speed. Although the molecules in a sample of gas have an average kinetic energy and hence an average speed, the individual molecules move at varying speeds. The moving molecules collide frequently with other molecules. Momentum is conserved in each collision, but one of the colliding molecules might be deflected off of a high speed while the other is nearly stopped. The result is that molecules at any instant have a wide range of speeds. Figure 10.18 illustrates the distribution of molecular speeds for nitrogen gas at 0 Celsius, blue line, and 100 Celsius, red line. The curve shows the fraction of molecules moving at each speed. At higher temperatures, a larger fraction of molecules moves at greater speeds. The distribution curve has shifted to the right towards higher speeds and hence towards higher average kinetic energy. The peak of each curve represents the most probable speed, the speed of the largest number of molecules. Notice that the blue curve at 0 Celsius has a peak about 4 times 10 to the second meters per second, whereas the red curve at 100 has a peak at a higher speed of 5 times 10 to the 2 meters per second. Figure 10.18 also shows the value of the root mean square speed, u, of the molecules at each temperature. This quantity is the speed of a molecule possessing average kinetic energy. The RMS speed is not quite the same as the average mean speed. The difference between the two, however, is small. Notice that the root mean square speed is higher at 100 than at 0. Notice also that the distribution curve broadens as we go to a higher temperature. The root mean square speed is important because the average kinetic energy of the gas molecule in a sample is related to the square of u. Where u is the mass of the individual molecule, mass does not change with temperature. Thus, the increase in the average kinetic energy of the temperature implies that the root mean square speed, also the average speed of molecules, likewise increases as temperature increases. Figure 10.18. The effect of temperature on molecular speeds. Distribution of the molecular speeds for nitrogen at 0 Celsius, blue line, and 100 degrees Celsius, red line. Increasing temperature increases the most probable speed, curve maximum, and the root mean speed, U, which is indicated by the vertical dashed line. Application to the gas laws. The empirical observations of gas properties as expressed by the various gas laws are readily understood in terms of the kinetic molecular theory. The following examples illustrate the point. 1. Effect of a volume increase at constant temperature. A constant temperature means that the average kinetic energy of gas molecules remain unchanged. This in turn means that the root mean square speed of the molecules, U, is unchanged. If the volume is increased, however, the molecules must move longer distance between collisions. Consequently, there are fewer collisions per unit time with the container walls, and pressure decreases. Thus, the model accounts for a simple way for Boyle's law. 2. Effective temperature increase on constant volume. An increase in temperature means an increase in the average kinetic energy of the molecules, and thus an increase in U. If there is no change in volume, there will be more collisions with the wall per unit time. Furthermore, the change in momentum in each collision increases. The molecules strike with walls more forcibly. Hence, the model explains the observed pressure increase.